bays, and other roads and structures. A significant percentage of these have deteriorated or will begin to deteriorate in the near future. Much of this deterioration is due to the action of de-icing salt, which penetrates the concrete cover and initiates corrosion of the reinforcing steel. The resulting rust causes the concrete to delaminate and spall, leading eventually to severe deterioration of the riding surface. Many of the most severely damaged bridge decks require total replacement because they're no longer capable of safely carrying today's heavy traffic loads. Other decks may have to be replaced because they're too narrow or are otherwise obsolete in terms of their function. Excessive deterioration may indicate that only total replacement would be cost-effective. So a visual survey is the first and most important test, including a close examination underneath. This is especially important if there's been an asphalt overlay. After a visual survey is completed, the deck should be sounded to locate any subsurface delaminations. Extensive delamination may indicate the need for deck replacement. Delaminations may also be detected with more sophisticated techniques, such as infrared thermography, impact echo measurements, and ground-penetrating radar. Half-cell potential measurements are often used as part of the deck survey when bridges are chosen for rehabilitation and overlays. The electrical potential measured between the copper sulfate half-cell and the rebar steel is an indication of the probability that the rebar steel is corroding at any given location. Large areas of potential values that are more negative than 350 millivolts indicate that the deck is a good candidate for rehabilitation. Sampling for chloride analysis is another widely used measurement in deck surveys. Powder samples are obtained using an impact hammer and are then analyzed in a laboratory. Samples can also be analyzed in the field using a new technique developed by Sharp. Chloride contents in excess of 1 to 2 pounds per cubic yard of concrete are usually sufficient to initiate corrosion of rebar steel. Some agencies may require removal of all chloride-contaminated concrete prior to installation of an overlay. This will prolong the life of the overlay because corrosion will not continue in the absence of chloride. All of these measurements can be used in a decision model to determine the most cost-effective strategy for deck rehabilitation. This computer-based model is available from Sharp. Now let's look at materials. There are various types and systems of materials which have been used to overlay reinforced concrete bridge decks. These include latex modified concrete, or LMC, silica fume concrete, or SFC, low slump dense concrete, LSDC, low water cement ratio concrete, LW/C, and polymer concretes, PC. Conventional Portland cement concrete has also been used to overlay bridge decks. Because LMC and SFC are the most widely used, we'll concentrate on these two types. Latex-modified concretes contain a latex emulsion, generally based on styrene butadiene polymer, which is added to the concrete mix. A typical mix might contain 658 pounds of cement per cubic yard, 15% latex solids by weight of cement, fine and coarse aggregates, and enough water to reach a slump of 4 to 6 inches. The water-to-cement ratio should be no greater than 4/10. Air entrainment is not required. The LMC is mixed in mobile concrete mixers and placed at a nominal minimum thickness of 1 1/4 inches. Silica fume concretes contain a very finely divided material which is a byproduct of silicon or ferrosilicon alloy production. Silica fume is available in slurry and densified powder forms. These concretes normally contain from 600 to 700 pounds of cement per cubic yard, 7 to 10% silica fume by weight of cement, fine and coarse aggregates, and air entraining and water-reducing admixtures. The water to cement plus silica fume ratio should be no greater than 36 hundredths. Superplasticizer must be added to obtain the desired slump in the range of 4 to 8 inches. SFC is produced using conventional ready-mix truck operations. After the deck has been selected for overlay, the next step is surface preparation. All deteriorated, delaminated, and spalled concrete must be removed, and the surface must be properly cleaned prior to placing the overlay. Most often the process begins by scarifying the top surface of the deck to a depth of at least 1/4 inch. Scarification using automatic rotomilling equipment must be done carefully so as not to damage any steel lying close to the surface of the deck. Also, because the equipment is not capable of reaching all areas of the deck, considerable handwork may be needed near curbs and joints. In lieu of mechanical scarification, a process known as hydrodemolition can be used to prepare the deck surface. This technique involves applying water at pressures up to 20,000 psi to cut grooves at regular intervals across the concrete surface. The high pressure of the water also breaks off the concrete remaining between the grooves, removing all concrete to a preset depth. The unit is robot controlled and can process up to 100 square feet of surface per hour. The equipment can be used to selectively remove only deteriorated concrete. However, in preparation for rigid overlays, it's simpler to remove concrete to the depth anticipated for the overlay. This allows the contractor to place the overlay up to the grade of the original deck. That way, existing drains and joints can remain at their original elevations. One of the major advantages of hydrodemolition is that all deteriorated concrete surrounding reinforcing bars is removed during the process. So chipping hammers are needed only to obtain minimum clearances. This results in labor savings and prevents damage to the bars. After the top layer of concrete is removed, the deck should again be sounded to identify any deeper delaminated areas. These areas are then marked with paint, and the concrete is removed using small chipping hammers. The hammer should weigh no more than 30 pounds, and the angle of the hammer should be less than 45 degrees to the surface. The contractor has to be very careful not to damage any exposed steel. If the bond between concrete and steel has been destroyed, or if more than half of the bar has been exposed, the concrete should be chipped away from the steel to a clearance of at least 3/4 of an inch. After all of the deteriorated concrete has been removed, the remaining concrete and exposed steel should be blast cleaned. All contaminants, dirt, and loose rust must be removed so that a good bond between the overlay and the substrate may be obtained. High-pressure water blasting can also be used. This final cleaning must be done no earlier than 48 hours before placing the overlay. The surface should now be thoroughly checked for the presence of any material which could interfere with bonding. A good way to check for loose material is to use black electrical tape. Just press the tape onto the surface and then examine the sticky side. If the tape picks up any particles, the surface should be cleaned again with dry compressed air. During the cleaning process, the contractor will begin setting the rails for the paver. The rails are positioned outside the width to be paved on a curb, sidewalk, or median barrier. They should be supported by adjustable rail supports. No discernible deflections of the rails should be permitted. The next step is to dry run the finishing machine across the full length of the lane to be paved. The minimum overlay thickness should be verified by numerous clearance checks during the run. Also, the vibration frequency of the screed should be checked with the vibratory tachometer during the run. After all corrections are carried out, a final test run should be made. On the scheduled day of placement, you should check the ambient conditions to see that they comply with agency specifications. Many agencies use this chart to determine the evaporation rate from the concrete. Determining the evaporation rate involves measuring the ambient air and concrete temperatures, wind speed, and relative humidity. Concrete temperature can be measured in the shade using concrete thermometers or thermal probes. Wind speed can be measured with a small portable anemometer. Relative humidity can be measured with a traditional sling psychrometer or with new digital units. Suggested maximum limits on evaporation rate range from 1/10 to 1/1500 pounds of water per square foot per hour for LMC and SFC overlays. If the actual rate exceeds these limits, consideration should be given to placement at night when temperatures are lower, or taking precautions such as using windscreens or fog sprays. Normally, there are also limits on minimum air temperatures for placement. Generally, overlays should not be placed when ambient temperatures are expected to fall below 45 degrees Fahrenheit during the period of placement and curing. The final step of preparation is to saturate the deck and then allow it to come to a surface dry condition. Wetting is normally done from 2 to 3 hours before placement. Once the surface is dry, the deck is ready for placement of the overlay. Latex modified concretes are generally produced using mobile concrete mixers. These are essentially mobile concrete mixing plants with output capacities of from 3 to 12 cubic yards. The dry materials are stored separately in hoppers on the mobile mixer. The water and liquid admixtures are stored in tanks. The materials are then fed through vibrating gates onto a conveyor belt that transports the material to an auger mixer at the front of the unit. The mobile mixer must be calibrated prior to use. This is done by discharging materials and measuring the amount of time needed to discharge the desired weights. All discharge rates are based on the rate of cement discharge. Now we're ready for the LMC overlay placement. A bonding grout should be broomed into the deck immediately in front of the area to be overlaid. The grout can be composed of sand and cement paste broomed out of the actual LMC, or it may be prepared separately. In any case, it must not be allowed to dry out before the LMC is placed on top of it. LMC is then discharged from the mobile mixer and placed in front of the paver. A roll of concrete should be maintained in front of the screed. You should check the vibration frequency of the screed again, now that the screed is under load. In variable depth areas, more than 3 inches deep, internal vibrators should be used in advance of the screed. The paver cannot finish the entire width of the deck. so areas near curbs and joints must be carefully hand finished. Throughout the placement operation, a 10-foot straight edge should be used to check the plainness of the surface. Thickness checks should also be made frequently. After the overlay is consolidated and screeded, the surface must be textured. This is normally done with a turf drag or a large wire broom that produces transverse tines ranging from 1/8 to 3/16 of an inch in depth and spaced at about 3/4 of an inch. The areas near the curbs are usually left untextured. Problems can result when too much time is allowed between placement of concrete and curing. Ideally, elapsed time should be no longer than 10 minutes, so all work should be done rapidly, but with great care. Timely and proper curing is essential for construction of durable LMC overlays. Wet burlap, kept continuously moist with soaker hoses and covered with thick polyfilm, is the preferred method of cure. After the first 24 hours, the burlap is removed and the overlay is allowed to air cure for 3 additional days. Construction of bridge deck overlays using silica fumed concrete is virtually identical to that of LMC overlays, with the exception that mobile mixers are not generally used. Instead, conventional ready-mix trucks are used to transport either central or truck-mixed silica fumed concrete to the job. Since the ready-mix trucks will deposit concrete immediately in front of the paver, it's important that the deck surface be protected from any contaminants that may drip off them. This can be done with plastic sheeting or dry burlap mats placed on the deck, or cloths may be attached underneath trucks to catch any drippings. SFC overlays are also very susceptible to rapid drying and cracking. Curing must be initiated immediately after the tining operation so that exposure of the surface to the dry air is minimized. SFC must be moist cured for the full curing period. This should consist of at least 3 days of wet cure under soaked burlap covered with polyfilm. Provisions must be made to keep the burlap continuously wet. Longer wet cure periods are desirable. We have seen how decks are selected and prepared for concrete overlays. By closely controlling the quality throughout preparation, placement, and curing, these overlays will add many